In this video, we're going to talk about, we're going to continue talking about factoring. We're going to start out with some special types of factoring. And then we're going to add in kind of a summary, and we're going to talk about how to solve an equation by factoring. Okay, so this is sort of a continuation from the last video. We started talking about factoring. I like to break my factoring strategies into 4 types, I guess. The first would be the greatest common factor, or the GCF. Then if I have 4 terms, I'm going to factor by grouping, which is the second strategy. Trinomials have 3 terms. So in the last video, we looked at both using the trial and error and the AC method to do factoring a trinomial. I'm going to add to that now some special types of factoring. I'm not changing the 2 methods that are listed here. I'm just going to show you some examples where when I use trial and error or when I use the AC method, I get a special result. So we're going to do that first, and then we're going to add the 4th category, which is factoring binomials, so 2 terms. Okay, so the first special category under the trinomial heading are called perfect square trinomials. So a lot of people like to look at a pattern or identify a pattern. So if you're a pattern person, what I think indicates the pattern, I guess, is we have 2 perfect squares on either side, and then we have this like doubled middle term. So if I see that, when I factor it, I'm going to get 2 parentheses that actually look the same. If I get the same thing in both parentheses, I can write it as a square. I'm happy to accept either of these 2 answers, so I don't mind you leaving it as 2 separate parentheses, or I'm happy with you writing it as a square. Either one works just as good for me. So we could have that pattern show up with a plus in the middle, so both of them being a plus, or both of them being a minus. Let me give you a couple of examples of that. Let's start with this one. So say we had x squared plus 6x plus 9. Again, I don't have to do anything differently from what we've already talked about. I can factor it in the same way. So think about trial and error, I think would be good for this one, right? X and X for sure. 2 numbers that multiply to be 9 and add to be 6. 3 and 3 comes to mind. Because it's a positive 6, I'm going to make both of these a plus. That's a great answer, right? Just like that. Or if you want, because they match, you could write it as x plus 3 squared. Okay, how about a couple more? For the next one, this one actually has a GCF. It's good to think of GCF first. Remember we said that's why we listed it as the first type of factoring. So what do all of these 3 terms share? They all share an A. Okay, so let's do that as a first step. So if I factor out an A, what's left? 25A squared, 10 plus 10AB plus B squared. Okay, you could definitely use the AC method here if you wanted to. I'm going to use the trial and error method. Numbers that multiply to be 25 must be 5 and 5. Notice I have the A's in the front on this one, so it'd be 5A and 5A. Numbers that multiply to be B squared, it's just a 1B squared, so I'm going to go with B and B. On the outside, I'm going to have 5AB, and on the inside, I'm going to have 5AB. And those are going to add up to 10ab as long as they're positive. Okay, so there's that pattern again. Maybe you identified this as a perfect square of 5a. Okay, and this is a perfect square of b. So this is that double of 5ab. If you're a pattern person, maybe you recognize that. If not, maybe you worked it out as you tried to factor. Okay, same thing for this one. Do you want to try and use the AC method here? Why don't we do that? So A times C would be 4. 4 could be 1 times 4 or 2 times 2. We need to pick the pair that adds to be -4. I think 2 and 2 will work if we make them both negative. So that means we could rewrite this as 4z squared minus 2z minus another 2z plus 1. So now I want to use factoring by grouping. So I'm going to pair them up. What would be the GCF of the first pair? Looks like 2z. And I'll have a 2z minus 1 left over. What's going to be the GCF for the second pair? They don't share anything. Okay, so that means their GCF is 1. If there's nothing that they have in common, everything always shares a 1 in common. And since I'd rather this be a positive 2z, I'm going to factor it out as a -1. So that's going to change the sign to make this 2z. It's going to make this a -1. Notice they both have the same parentheses, 2z minus 1. And what's left is a 2z and a -1. So you can either leave it like this or you can write it as a square, just like we did up here. Right? So this is a fine answer, or if you want to write it as 2z minus 1 squared, you can do that as well. Okay, so those are perfect square trinomials. This is a special pattern, same strategy, where I happen to get the same parentheses. All right, so now we're going to look at the next category, which is factoring binomials. There are actually several special types of factoring that fall into this category. So binomials have 2 terms. I always recommend you look to see if there's a GCF first. Sometimes, even if I have 2 terms, the only type of factoring I can do is a GCF. So if you can remember to check that first, that'll help you out. If it's not a GCF, it might be one of these other 3 types. And so we're going to list these out one by one. The first one is the difference of 2 squares. So this is 2 perfect squares. Difference here means subtraction, right? This is that special kind of multiplying that we were mentioning in the first video in this chapter, right? Where I have one parentheses that has a plus and one that has a minus. The reason this works, let's just do this real quick. If we FOIL this out, we'll have x squared. Outside, we'll have minus xy. Inside, we'll have plus xy. And then minus y squared. This is unique because the middle terms add to 0 and cancel out. Okay, and that only happens with this pattern. So if I have a result that doesn't have a middle term, if I have perfect squares, then it's going to factor, one with a plus, one with a minus. Okay, for example, x squared minus 36 would factor to be what? I could still do x and x. I could still do the trial and error method, right? Two numbers that multiply to be 36, but add to be 0 because I have no middle term. So one with a plus, one with a minus. Okay, this is a good time to point out that we don't have a sum of squares factoring method. So this, for now, we're going to say it's not factorable. To factor it, I'd have to use a complex number. Okay, we don't usually do that until pre-calculus. Okay, so you can hold off on that for now. Or if you're really curious, you can go think about some i's and how you would factor that, right? All right, I think I have a couple more. This one actually has a GCF. So what do these two terms share? They both have a z squared. Right? Maybe you saw that at the beginning, maybe you didn't. If you didn't do it right away, you could definitely do it second. You can do the factoring steps in either order, but it's a lot easier to spot usually at the beginning. Now I have two perfect squares, right? So what's going to go in the front? 8z and 8z. And what's going to go in the back? 49 is 7 times 7. No middle term, so one with a plus, one with a minus. All right, here's a weird one. This is a perfect square. It looks different, but it is something squared. And this is a perfect square. So this actually works for this too. It looks really weird, but I thought maybe it would be interesting to show you. So the first term, we're going to have x plus 1. If you're more comfortable with it being in parentheses, you can do that. Right, because x plus 1 times x plus 1 would be x plus 1 squared. In the back would be 5 and 5. One with a plus, one with a minus. But really we could calculate these. If we took off the parentheses, this is the same as x plus 6 and x minus 4. This type of problem always blows my mind a little bit. But it still kind of fits into this category if you wanted to think about it that way. We won't have too many of those, but I thought that would be interesting to show you. Okay, so that's difference of squares. We're talking about, let me do this, binomials. Two more categories in this, under this heading. The next two kind of go together, and they are perfect cubes. So for the cubes, we do have both the difference of cubes and the sum of cubes. Okay, so usually at the university level, they make you memorize these. I am not going to make you memorize these. I'm going to give you these on the test. So you'll know what they are. You just need to make sure you can use them appropriately. If you wanted to memorize them, usually the acronym we use is SOAP, and this talks about the signs involved. Same sign, opposite sign, always positive. So for this first one, x cubed minus y cubed. The first parentheses, we just take off the cubes, and we have the same sign. The second parentheses, this looks like a perfect square trinomial, but I don't have the 2 or the doubled middle term. So I'll have x squared, opposite sign, so plus now, xy, and then always positive, plus y squared. Same thing for sum of cubes, it's a plus. First parentheses, I take off the cubes with the same sign. And I have x squared, opposite sign, and then always positive. All right, so let's try a couple of these just to make sure you know how it works. This one is a sum of cubes. This one is nice because x is in the same place, right? This is x cubed and this is x cubed, so I'm going to be using this formula. Instead of the y cubed, I have 27. So let's write it down here. So this is x cubed plus 27 is 3 cubed. So I'm going to be using this sum of cubes formula, mainly because I have a plus here. But everywhere there's a y, I'm going to be replacing it with a 3, right? Because instead of y cubed, I have 3 cubed. So the first parentheses, I take off the cubes, so I'll have x plus, instead of y, I'm going to put in the 3. Then I'll have x squared. Minus x times y will be minus x times 3, or 3x, plus y squared. Instead of y, I'm going to put in 3, so plus 3 squared would be 9. Okay, usually if we factor with a sum or a difference of cubes, we're done. You could check to see if this were factorable any further, but I don't think I've seen a problem yet where it was. It could happen, but I haven't seen one. Okay, so usually we're done. Let's try one more. All right, let's identify the perfect cubes. So this is the perfect cube of 5x. 1 is the perfect cube of itself. So I'm going to pull down the formula in a second, but instead of x, I'm going to be replacing the x with 5x. And I'm going to be replacing the y in the formula with a 1. This time, can I fit it all on one screen? Barely. Okay, this time we're using the difference because we have a subtraction in the middle. So my first step is to just take off the cubes, so I'll have 5x minus 1. I'm going to write this one in a couple of steps. So next piece would be x squared, but I'm replacing x with 5x. So it's actually 5x squared plus x times y. So plus 5x times 1 plus y squared. So plus 1 squared. Okay, so now let's make it look nice. So this is 5x minus 1. 5x, if I square the 5 and square the x, this is 25x squared. 5x times 1 is 5x. And 1 squared is 1. Okay, if you wanted to check yourself, you could definitely multiply this back out. And a lot of things should cancel and you should get back to your original expression. All right, so this is the sum and difference of cubes. I definitely want to encourage you to try this out. Go find a couple examples, put the formulas right by you and make sure you can use them. Watching me do it and doing it yourself, we've already discussed, are two very different things. So go find examples and try this out for yourself. It's not hard, but it is something you need to do on your own to make sure you have it. Okay, so that's all the categories that we've looked at so far. So here is kind of a copy of what's in your book as far as a summary. just to run through this one more time. So factoring a GCF is a good first step. Then you can choose a strategy based on how many terms you have. If you have 4 terms, grouping would be a good strategy. If you have 3 terms, so a trinomial, the trial and error method is good, or the AC method. If you have 2 terms, it could be a perfect squares, so difference of squares, or sum or difference of cubes. It is good to check that your answer is completely factored. So once you've factored it, you might want to double check that the factors you have in the parentheses do not have any common factors. If they do, you need to factor those out. Okay, so I've chosen a couple examples that the directions usually say factor completely, which means there's more than one type of factoring involved. So let's try this one. So first we have, remember we said first would be good to check to see if we have a GCF. Do we have a GCF here? For sure we do, right? A number that goes into 30, into 3, and into 9 would be 3. How many x's do these all share? 2 x's. If I divide 3x squared out front, I'm going to be left with 10x squared plus x minus 3. Okay, factor completely means probably I'm not done, and I'm not. So the 3x squared part is done. Now I want to look at what's left and see if I can factor this further. So this is a trinomial. So the trial and error method or the AC method would be good. Okay, I'll leave that up to you, either one. I'm going to use the AC method just because I think a lot of you would want to see that. And I'm going to write my result right here, but I'm going to kind of do it off to the side so that it doesn't get confusing in here. So let's do that. If you want to do the trial and error method, you go right ahead. I will say that as you get more and more practice, the trial and error method is going to be faster. So it would be really good for you to move in that direction if you can. A times C would be negative 30. Factors of 30, let's say, 1 and 30, 2 and 15, 3 and 10, 4 doesn't work, 5 and 6, the next number would be 6, but we have a 6 already, so we're done. We need numbers that, because it's negative, we need them to really subtract to be 1x, right? I think this is going to work. It's a positive one, so we want the 5 to be negative. So we'll write this as 10x squared minus 5x plus 6x minus 3. Then we'll factor by grouping. The GCF of the first pair would be 5x. So I'll have a 2x minus 1 left over. Notice all of the 5x is factored out front. And so I need this 1 to kind of hold the place so that if I were to multiply it back out, I would still get this 5x. GCF here would be a 3. And when I divide that out, I'll have another 2x minus 1 left over. 2x minus 1 is in common. And I'll have a 5x and a plus 3 in the second factor. So I'll transfer those up here. And this will be our final answer. Okay, I actually have several examples of these here for you to try. I'm just going to do one more. This one is also factoring by grouping, and we know that because there are 4 terms. It would still be good to take a second and look to see, is there a GCF? But in this case, there's not. Okay, so I'm going to go straight to grouping. And I'm going to put the negative in the middle into the second pair. The GCF of the first pair would be x squared. The second pair, and I think we've already seen this once before, but these do not share anything in common. So if there's no GCF, there's always a 1. And because this is negative, I'm going to make it a -1. That's going to make this change sign so that it's 2x minus 3. Now they both have a 2x minus 3. So I'm going to factor that out. And I'm left with x squared minus 1. Anything with an x to the first power, that's just an x, or x to the power of 1, is done. I cannot factor this piece anymore. But I can factor this piece. So I would want to check that. Sometimes it'll be a yes, and sometimes it'll be a no. This time it's a yes, right? So I'm going to leave this 2x minus 3, and I'm going to break this up. What kind of factoring can we use here? This is a difference of squares, right? 1 is a perfect square. X squared is a perfect square. So this is an x, 1 and 1. There's no middle term, so 1 with a plus, 1 with a minus. Now all 3 parts have x to the first, which means we really can't go any farther. That's as much as we can do. I'm going to leave the other 2 examples here in the outline for you to try on your own. Let's take a look at solving equations, and that'll kind of round out our video. Okay, so now that we've talked about factoring fully, we want to put it to use, right? This is one of the methods that we'll use to solve an equation that has an x squared or maybe even a higher power. What we're going to need to do, and I don't actually have this written here, so I'm going to add it, is we need to get 0 on one side. Then we're going to factor. Oh, I guess I do have that down here, don't I? With the triple exclamation point. And then we're going to set each part of our factoring equal to 0 using this 0 product property. Okay, so we're going to start simple, right? Everything actually is done for us. 0 is already on one side. It's already been factored. So really, for this first example, we're just practicing this extra step that we use when we solve an equation. And that is to set each part equal to 0. So the 2 factors, x plus 2 and x minus 4, we set them individually equal to 0, and then we work that out. So to solve for x, I would subtract 2 on both sides, add 4 to both sides, so I get 2 answers here, and you could just leave your answers like this. That's totally fine with me. If you want to be fancy, you can put them in the squiggly brackets. Okay, let me show you a couple more. So this next one, remember the first step we said was we want to get 0 on one side. So we want to move everything over. So let's move this 14x over to the left by adding. When we add it to the other side, we want to write that left-hand side in the way that we're used to seeing it, right? With descending powers of x. So I'm going to squeeze it in the middle. Okay, so we have 0 on one side. Now we want to factor. I need two numbers that multiply to be 49 and add to be 14. 7 and 7, so it's going to work. It's a positive 14, so 2 pluses. Then the last step is just to set each of these equal to 0. This time they're the same, right? So that's kind of redundant. I don't have to do it twice. I can just do it once because I'm going to get the same answer repeated. So I get one answer, x equals -7. All right, how about one more? This time we're solving with x cubed, but that's okay because we can still use factoring to do it. What kind of factoring should we use? Yeah, factoring by grouping, because we have 4 terms. So let's pair them up. The GCF for the first pair would be x squared. The GCF for the second pair would be -4. Sorry. Okay, they both have an x plus 7, so I'm going to factor that out. And when I divide that out, I'll have x squared left from the first term and -4 from the second term. Okay, I could solve from here, but I could also keep factoring. Since this is a factoring video, we're going to keep factoring. Like we just said, if it's x to the first, I can't break this down anymore. But if it's an x squared, I might be able to break it down. And this is, just like the one we did a minute ago, this is a difference of squares. So let's break that up. Okay, since we're solving an equation, the last step would be to set each part equal to 0. I'm going to continue to write that out for now, but you could definitely do this part in your head as time goes on, right? So notice we get 3 answers this time. If I have a degree of 3, that means I could have at most 3 answers. And that's another thing that's going to come up in college algebra when you get there. All right. So So I'm sorry this went a little long, but I hope this kind of wrapped up the factoring idea for you. So just to summarize what we've looked at in this video, we talked about trinomials that had a special pattern. We still used the trial and error in the AC method, but we got a special result, and we talked about that. We talked about factoring with two terms, a binomial, either the difference of squares or the sum or difference of perfect cubes, and there we have formulas for that. Then we looked at a summary of how to decide when to use which factoring strategy, and we did a couple of examples that had multiple factoring types, and then we just finished solving equations by factoring. All right, so for sure, take some time to practice your factoring. The more you practice, the better you'll get at it, I promise. Good luck, and we'll see you in the next video.